Now we will discuss N-type semiconductor and P-type semiconductor. As you know very well that the electrical conductivity of pure semiconductor, that is intrinsic semiconductor, is very small at room temperature. So that's why they are not that much useful while designing the semiconductor devices. So anyhow we must have to increase the electrical conductivity of pure semiconductor, and that can be done by using a doping. In doping, few atoms, maybe from 5th group of periodic table, maybe from 3rd group of periodic table, they were added as an impurity to a pure silicon or germanium crystal. So the resultant doped germanium or silicon crystal is called doped semiconductor, or it is also known as extrinsic semiconductors. Now these extrinsic semiconductor, it may be N-type semiconductor when free electrons are available as a majority charge carrier and they are responsible for conduction of electricity through them. Whereas the extrinsic semiconductor, it may be P-type semiconductor whenever holes, that is effective positive charges, are the majority charge carrier in that extrinsic semiconductor, which are responsible for conduction of electricity. Then how to construct N-type semiconductor and that of P-type semiconductor? As far as construction of N-type semiconductor is concerned, whenever in a pure silicon or germanium, whenever in a pure silicon or germanium, which is a pure semiconductor, when it is doped with pentavalent impurity such as phosphorus, arsenic or antimony, when few atoms maybe of antimony were added as an impurity to a pure silicon crystal, then we will get N-type semiconductor. So the extrinsic semiconductor, which is doped with pentavalent impurity atom, are called N-type of semiconductor, or when a germanium or silicon is doped with pentavalent impurity atom, then we will get N-type of semiconductor. As an example of pentavalent impurity, phosphorus, arsenic and that of antimony. Remember, as far as antimony is concerned, what is the atomic number of antimony? 51. Then the schematic electronic structure of antimony will be like this: 2, 8, 18, 18, and in the last orbit only 5 electrons are left, means the valency of antimony is 5. Valency of antimony is 5. And when this pentavalent impurity atom, that is antimony atom, were added as an impurity to a pure silicon crystal, then the atom of antimony will acquire the position of one of the silicon atom. Already that antimony has 5 electrons in its outermost orbit, means in order to become, or in order to satisfy the stable electronic configuration, actually antimony needs only 3 electrons. But due to crystal structure of silicon, this antimony atom will share 1 electron each from 4 of its neighboring germanium atom, and it will form 4 strong covalent bond with 4 of its neighboring silicon atom. And as far as that 5th valence electron of antimony is concerned, see here, antimony has 5 electrons, valence electron, 4 of which were used in the formation of what? 4 strong covalent bond, because it shares 1 electron each from 4 of its neighboring silicon atom. So that 5th valence electron of antimony, it is loosely bound with nucleus of antimony, and this 5th valence electron of antimony, it can be made free for conduction of electricity, provided that 5th valence electron has given a very small amount of energy. It may be 0.05 electron volt when antimony is added to what? A silicon crystal, or it may be 0.01 electron volt when antimony is added to what? A pure germanium crystal. Pure germanium crystal. Remember that whenever one impurity atom, one pentavalent impurity atom is added to a pure germanium crystal, that one impurity atom will donate one free electron. One impurity atom will donate what? One free electron, and that free electron is available for conduction of electricity. Free electron is available for what? Conduction of electricity. Remember, in case when silicon crystal is doped with pentavalent impurity, when few atoms of pentavalent element were added as an impurity to a semiconductor like silicon, then in that doped semiconductor, large number of free electrons are made available in the conduction band, and they are available for conduction of electricity. And because here any pentavalent doped semiconductor, any pentavalent doped semiconductor will have large number of free electrons in it, means electrons are the majority charge carriers. These electrons are available in what? The conduction band. Means conduction of electricity is mainly due to electrons which are negatively charged particle. So such type of semiconductors, they are called as N-type semiconductor. N means negative. So whenever electrical conductivity is due to what? The negative charge carriers, then such type of extrinsic semiconductors, they are called as what? N-type of semiconductor. They are called as N-type of semiconductor. Now in N-type of semiconductor, the free electrons which are available for conductions of electricity, they are produced mainly due to two reasons. Number one, the availability of free electron for conduction of electricity, it depends on the number of donor impurity atom added to it. More the number of donor impurity atom added to a silicon crystal, more will be the free electrons available for conduction of electricity. In addition to this, electron hole pairs are produced. See here, when we are having a doped silicon crystal at room temperature, we know that these covalent bond at absolute zero temperature, covalent bonds are strong and no electrons were available free for conduction of electricity. But at room temperature, these covalent bonds, few of the covalent bonds, they will be broken as they receive the thermal energy. And when few of the covalent bonds were broken thermally, they will create electron hole pair. Means in addition to the number of free electrons available by donor impurity atom, we are having the availability of free electrons due to what? Due to breakdown of few of the covalent bonds due to thermal agitation. And remember that as far as that doped silicon crystal is concerned, there is a recombination of electrons and hole pair, because they are what? Oppositely charged particle. And if I say that Ne represent the number of free electrons per unit volume, that is number density of free electron. Ne represent what? Number density of free electron, means the number of free electrons per unit volume, and NH represent the number density of holes, that is number density of what? Vacancy of electron or presence of positive charge, effective positive charge. So Ne represent number density of free electron and NH represent number density of free holes. And remember number density of, as far as holes are concerned, they are produced mainly or only due to what? Only due to thermal breakdown of few of the covalent bonds. So naturally NH is very less than Ne, means Ne is very greater than NH. That is, in case when silicon is doped with pentavalent impurity atom, then the number of free electrons per unit volume, they are very large as compared to that of number of what? Free holes, as compared to that of number of free holes. Means in a germanium or silicon which is doped with pentavalent impurity atom, electrons are the majority charge carriers while holes are the minority charge carriers. Remember, in a germanium or a silicon which is doped with pentavalent impurity atom, electrons are the majority charge carriers while holes are the minority charge carrier. Holes are the minority charge carrier. Now look at this. When antimony atom is added as an impurity to a pure silicon crystal, then as far as that fifth valence electron of antimony is concerned, what is the energy level of fifth valence electron of antimony? That fifth valence electron of antimony has an energy level which is lying in what? The band gap, and it is near to that of a conduction band. Means whenever impurity atom donates the electron, these donated electron will have an energy level which is lying in the energy gap, and it is near to that of conduction band, so that on receiving a very small amount of energy, 0.05 electron volt energy, these electrons, they can be easily made available for conduction of an electricity. So you remember that as far as extrinsic semiconductors are concerned, their conductivity is much better than that of any intrinsic semiconductor. Their conductivity, it must be what? Much better than the intrinsic semiconductor. Now you may think, what amount of impurity atom must be added to a pure silicon crystal? Remember that whether we are having a metal or a semiconductor, if I just count how many atoms are present in 1 cubic centimeter of metal or 1 cubic centimeter of semiconductor, 1 cubic centimeter of metal or 1 cubic centimeter of a semiconductor, they will contain nearly 10 to the power 22 number of atoms. And as far as the metals are concerned, every metal at least will donate one electron as a free electron. Means in case of metal, what you can say, that in 1 cubic centimeter of metal, how many free electrons are available? 10 to the power 22 free electrons are available for conduction of electricity. But if I just consider 1 cubic centimeter of germanium, 1 cubic centimeter of germanium at 20 degrees Celsius, at 20 degrees Celsius, then the number of atoms in it, they are 4.2 into 10 to the power 22. Means if we are having a crystal of germanium whose volume is what? 1 cubic centimeter, and if I count how many germanium atoms are present in that 1 cubic centimeter, they were found to be 4.2 into 10 to the power 22. Then how many free holes and how many free electrons are available for conduction of electricity? So if I count it, then the free electrons in 1 cubic centimeter of germanium, it is 2.5 into 10 to the power 13, and free holes in 1 cubic centimeter of germanium, they are again 2.5 into 10 to the power 13, as compared to that of 10 to the power 22 number of free electrons in 1 cubic centimeter of any metal. Here the number of free holes and number of free electrons, they are 10 to the power 23, they are very less. Means anyhow, to increase the electrical conductivity of germanium, if 0.001% of impurity like arsenic were added to that germanium crystal, then how many free electrons were donated by this impurity which is arsenic? It will donate 10 to the power 17. Such a large amount of free electrons were made available, were donated by such a small amount of impurity to a germanium, and thereby it will increase the electrical conductivity of germanium by the factor what 10,000. Means if you add 0.001% of arsenic as an impurity to 1 cubic centimeter of germanium, then that impurity atom will donate 10 to the power 17 number of free electrons, and thereby it will increases the electrical conductivity of germanium by the factor which is 10,000, by the factor which is what 10,000. Remember that as far as n-type semiconductors are concerned, what are the features of n-type semiconductor? The first feature means you can write in a point that first feature, a material which is doped with pentavalent impurity, that is a donor atom, and the electrical conductivity of n-type semiconductor is mainly due to free electrons which are negatively charged particle, hence it is called n-type semiconductor. See what I am saying? N-type semiconductors are the materials, actually they are the semiconductors which are doped with pentavalent impurity, which are the donor impurity, which are what? The donor impurity. So you can define n-type semiconductor as what? The semiconductor material which are doped with pentavalent, that is the donor impurity, are called n-type semiconductor. The second point, the electrical conductivity of n-type semiconductor is mainly due to free electrons which are negatively charged particle. That's why this type of semiconductor is called n-type of semiconductor. N-type of semiconductor. Now during the construction of n-type semiconductor, here this donor atom will donate free electron and it becomes what? Positively charged ion. So as a donor atom donates or leaves the electron, and hence it becomes what? Positively charged ions. In case of n-type semiconductor, the density of free electron is much greater than that of density of free electrons, is much greater than that of what? Density of free holes. That is the number of free electrons per unit volume, they are very large as compared to that of what? Number of free holes. Means in n-type semiconductor, electrons are the majority charge carrier while holes are the minority charge carrier. And when any, last point, when any n-type semiconductor were given the energy externally, you may apply the electric field externally. So to any n-type semiconductor, when energy is given externally, then two types of charge carriers were produced. Number one, free electrons were produced, but the number of free electrons, they are what? Majority charge carrier, as well as the free holes are also produced, but they behave like what? The minority charge carriers. So on applying an energy externally to n-type semiconductor, two types of charge carriers were made available for conduction of electricity. First, free electron as a majority charge carrier, and second, free hole as a minority charge carrier. So this is all about n-type semiconductor. Now we will discuss about p-type semiconductor. Let us now discuss p-type semiconductor, just like n-type semiconductor. Now whenever pure germanium or silicon, it is doped with trivalent impurity such as boron, aluminium or indium, these are the trivalent element. Means when any pure germanium or silicon crystal is doped with trivalent impurity, then we will get p-type of semiconductor. As an example, let us consider boron, which belongs to third group of periodic table, Boron is what? It is a trivalent impurity, and because it belongs to third group of periodic table, it means valency of boron is 3. Means how many valence electrons are there as far as boron is concerned? Because boron has only 3 electrons in its outermost orbit, one can say that valency of boron is 3. Valency of boron is what? 3. Now let us see that how to construct a p-type semiconductor. To construct p-type semiconductor, a trivalent impurity such as boron, atom of boron is added as an impurity to a pure silicon crystal lattice. Then what happens? That boron atom will acquire the position of one of the silicon atom, and due to crystalline lattice structure of silicon, every boron atom has to share 1 electron each from 4 of its neighboring germanium atom, whereas boron has only 3 electrons in its outermost orbit. So due to sharing of electron from neighboring silicon atom, here every boron atom will form 3 strong covalent bond with 3 of its neighboring neighboring silicon atom. Boron atom is forming 3 strong covalent bond with 3 of its neighboring silicon atom, whereas the formation of 4th covalent bond with 4th silicon atom is incomplete due to deficiency of electron in the formation of covalent bond. See what happens? Boron has 3 electrons, and let they are 1, 2 and that of 3. Boron share 1 electron each from 4 of its neighboring germanium atom, and suppose these are the shared electrons. Because here as far as the formation of covalent bond between this boron and silicon atom is concerned, here there is a deficiency or absence of an electron in the formation of covalent bond, means that covalent bond is incomplete. That covalent bond is incomplete. Remember that incomplete covalent bond, deficiency of electron means presence of hole. Hole is nothing but effective positive charge. So there is an incomplete 4th covalent bond. That incomplete covalent bond, it can be completed because this hole or vacancy of electron will share the electron. Suppose here we are having another silicon atom, and here suppose that this is the electron of that silicon atom. So this 4th covalent bond, which is incomplete, it can be completed by sharing an electron. Here the electron from neighboring silicon atom, it will jump and acquire the position of hole. So the 4th covalent bond, which is incomplete, can be completed just by sharing an electron from neighboring silicon atom. And remember that shared electron, the place, here is the place from where that electron is shared to make that 4th covalent bond complete. Remember the place from where electron is shared, here there is again a deficiency of electron, means a hole is created. So the place from where electron from the neighboring silicon atom is shared, they will create a hole at that place. They will create what? Hole at that place. So remember, as far as trivalent impurity is concerned, whenever a trivalent impurity atom is added to a pure silicon crystal, each trivalent impurity atom will create one hole. It will create what? One hole. Hole is nothing but effective positive charge, and as that hole will accept the electron, hence trivalent impurity, they are called as an acceptor impurity. Remember what I am saying? A trivalent impurity will create one hole. One trivalent impurity atom will create what? One hole. And that hole will accept the electron. Hence, trivalent impurity, it is known as an acceptor impurity. Remember that as far as trivalent doped silicon crystal is concerned, we are having a silicon crystal which is doped with a trivalent impurity. It means large number of holes are available for conduction of electricity. Any trivalent doped semiconductor crystal has large number of holes which are made available for conduction of electricity, and because here a trivalent doped semiconductor, as they are having hole as a majority charge carrier for conduction of electricity, and as holes are nothing but positively charged particle, therefore we call it as a p-type semiconductor. So what you can say, any trivalent doped semiconductor which has a large number of holes available for conduction of electricity, means holes are the majority charge carriers, or holes or effective positive charges are responsible for conduction of electricity. So that type of extrinsic semiconductor in which holes are the majority charge carriers, holes means positive charges are responsible for conduction of electricity, they are known as p-type of semiconductor. They are known as what? P-type of semiconductor. Now in case of p-type semiconductor, actually how many holes are present? Means if I say NH represent number density of hole, means NH represent number of holes present per unit volume, number of holes present per cubic centimeter, and Ne represent number of free electrons available per unit volume, or number of free electrons available per cubic centimeter. Remember here, as far as holes are concerned, in a doped trivalent semiconductor or in p-type semiconductor, holes are produced by two ways. Number one, number of holes per unit volume, it depends on how many number of impurity atom added to that semiconductor. Means the availability of holes in p-type semiconductor, it depends on number of impurity atoms, number of trivalent impurity atom added to it. More the trivalent impurity atom added, more will be the holes available for conduction of electricity. In addition to this, at room temperature, due to thermal agitation, few of the covalent bonds were broken, and due to breaking of few of the covalent bond, electron hole pairs are produced. Means holes are produced due to two reasons. The number of holes or number density of hole, it depends on number of trivalent impurity atom added to pure semiconductor. And second thing, electron hole pairs are produced due to thermal agitation. Few of the covalent bonds were broken, and they will create what? Electron hole pair. And if I say NH represent number density of hole, naturally holes are created due to two reasons. So number density of hole is very large as compared to that of number density of electron, because number of free electrons available for conduction of electricity, they are produced only due to what? Breaking of covalent bond when electron hole pairs are created. So naturally number of free electrons in p-type semiconductor, they are very small as compared to that of what? Number of holes, as compared to that of number of holes. So you remember, in case of p-type semiconductor, as NH is very greater than Ne, means number density of hole is much more greater than that of number density of electron, means holes are the majority charge carrier while electrons are the minority charge carrier, and the conduction of electricity is mainly due to hole, which are the effective positive charges. So such type of extrinsic semiconductor, it is called as P type of semiconductor. It is called as what? P type of semiconductor. So about the P type semiconductor, what point you have to remember? Holes are majority charge carrier while electrons are what? The minority charge carrier. Remember that as far as these holes are concerned, here I had shown the band structure of P type semiconductor, where I had shown valence band and conduction band. We know that as far as boron is concerned, it has only 3 electrons in its valence orbit, means electrons are present in valence band. In addition to these valence electron, hole is also present in valence band. Hole, which is an effective positive charge, is also present in valence band. But remember, the energy level of hole created by that impurity, trivalent impurity atom, the energy level of hole is lying in the band gap such that it is near to that of a valence band, so that electrons from the neighboring atom can occupy the hole and can be made available for conduction of electricity. So you remember one thing, that as far as the energy level of hole donated by what? A trivalent impurity is concerned, it is in between the energy gap and it is near to that of what? A valence band. Because energy level of hole is near to that of valence band, so the valence electron from the neighboring atom can jump and acquire the position of hole, and holes can be made available for conduction of electricity. Holes can be made available for conduction of electricity. Now as far as features of P-type semiconductors are concerned, just like we had discussed the features of N-type semiconductor, what you can say? P-type semiconductors, these are the semiconductor materials which are doped with trivalent impurity. Semiconductor material which are doped with trivalent impurity. Second point, the electrical conduction of P-type semiconductor is mainly due to hole which are positive charge particle. That's why it is known as a P-type semiconductor, because holes are majority charge carriers and electrons are what? The minority charge carriers. Remember the next point, that as far as the trivalent impurity is concerned, it creates an hole and which accept an electron. Because it leaves hole, and therefore this trivalent impurity, as it leaves hole, and it becomes what? Negatively charged ion. Next point, in case of P-type semiconductor, number density of hole is much more greater than that of number density of free electron, means number of holes per unit volume, they are very large as compared to that of number of free electrons per unit volume. Means in P-type semiconductor, holes are majority charge carriers while electrons are what? The minority charge carrier, and the conduction of electricity is mainly due to what? It is mainly due to holes which are positively charged particle. Remember, to any P-type semiconductor, when energy is supplied externally, then two types of charge carriers are created. It will create both holes as a majority charge carriers and free electrons as a minority charge carriers, and both these charge carriers, they are available for conduction of electricity, and because holes are majority charge carriers and electrons are minority charge carrier, means conduction of electricity is mainly due to the flow of holes which is a positive charge. Therefore, such type of extrinsic semiconductor in which holes are majority charge carriers and holes are responsible for conduction of electricity, therefore such type of semiconductors, they are called P-type of semiconductor. Let us now discuss what is charge neutrality of extrinsic semiconductor. Means, as far as any extrinsic semiconductor is concerned, whether it is N-type semiconductor or whether it is what? a p-type semiconductor, remember both n-type semiconductor as well as p-type semiconductor, they are electrically neutral. How you can say that n-type semiconductor is electrically neutral? See here, because in n-type semiconductor we know that the number density of free electron is very large as compared to that of number density of hole. Means number of free electrons per unit volume, they are larger as compared to that of number of holes per unit volume. Remember, in n-type semiconductor, the excess of free electron, they are mainly due to what? The donor impurity atom. Each donor impurity atom will donate one free electron. By donating one free electron, that donor impurity atom, it becomes positively charged ions. See what I am saying? That in n-type semiconductor, we are having excess of electron. And who is donating this electron? That donor impurity atom will donate the electron. And when donor impurity atom donates an electron, it becomes positively charged. It means, as far as that donor impurity atom is concerned, it is electrically neutral. Hence, n-type semiconductor is electrically neutral. Similarly, in case of p-type of semiconductor, we know that NH is very greater than Ne. That is, number density of hole is much greater as compared to that of number density of electron. That is, the number of holes per unit volume, they are larger as compared to that of number of free electrons per unit volume. Means, in p-type of extrinsic semiconductor, excess holes are there. Holes are nothing but positive charges. And who is creating these holes? That trivalent impurity atom, which is an acceptor impurity atom. As acceptor impurity atom creates a hole. Means each acceptor atom, by losing hole, it gets what? Negatively charged. Means acceptor atom is electrically neutral, donor impurity atom is electrically neutral, means n-type semiconductor as well as p-type semiconductor both are electrically neutral, even though n-type semiconductor has excess of electron, even though p-type semiconductor has what? Excess of hole. But because here donor impurity atom becomes what? Positively charged by donating an electron, and acceptor impurity atom, it becomes negatively charged by donating what? An hole. So in general, you can say n-type semiconductor as well as p-type semiconductor both are electrically neutral. And if I say Ni represent concentration of charge carriers, then Ni square, it must be equal to Nh into what? Ne. So you remember this formula while solving the examples on semiconductor regarding concentration of holes and electrons.